All right. Hello. It's 2 o'clock on Wednesday, and I'm here for the office hours. um, doesn't look like anyone's on yet, but I just got on, so guess I'm almost a minute late, but I guess it's still 2 o'clock, so I'm right on. I have a 2-year-old upstairs who wasn't wanting to go to sleep, so I had to go help him get ready. Anyway, um, for those of you who do come on, um, feel free to chat in the little chat window here on the live chat. A couple people have written in email questions, so I'll answer those. And then as people have either follow-up questions or uh, if you have questions that are about homework or anything else, just write them in the chat window. I'll go to the chat window ones first, and then I will go back to the email ones until we complete them all. Hopefully, we'll probably get through most of them. Anything's fair game. I mean, certainly, like if you want to go over things from class that or have been unclear, or if there's questions of the day that you haven't been able to answer or think about, or certainly like homework questions, please let me know, and we will go over those. And if you have just any other general questions about astronomy, last night, if you haven't already watched the YouTube thing from last night, many people last night just asked random questions about black holes and stuff. So I'm happy to answer things like that. So I'm going to get started with some of the email questions. One of the questions is, how can measurements of light explain the celestial compositions of bodies? And so the biggest thing about this one, where it really was going here, was very briefly, we talked at the end of last week. I showed you those like spectral tubes, and we saw that one of them was neon, the other one was actually xenon, if you saw it. But just taking the neon, you saw hopefully through the little diffraction grating that there was a specific pattern of lines. There was a bunch of red lines, some orange ones, a couple yellow ones, maybe even a green one, and that made that kind of red color. But when you spread out all the light, you saw it was individual lines. So that pattern of lines is different for every single element in the universe. So hydrogen looks different than helium, then looks different than oxygen, and so on and so forth. So that if you see that pattern of lines in, say, a star, then you know that that star has, say, hydrogen or neon or oxygen. And you could do that with a star. You can actually do that with a galaxy. And so that was the kind of context I wanted to give you, is that, we can look at the sun and see at least what's in the atmosphere of the sun by what we call the spectral features. What features, those lines, what those tell us about which elements are in the sun. Certainly that's true of galaxies, when we look out at galaxies. And you can actually even do this for like planets. You can play some tricks, like look at the sun reflecting off planets, and then some things are absorbed and some things aren't. So you can actually do this using this trick of light. But I think that's where the question is asking, is how do you use light to tell the kind of composition of objects? And use this concept of spectroscopy, or looking at what we did in those tubes. So hopefully that answers the question. The next question was, how can you explain the 4 stages of, can I explain the 4 stages of terrestrial planet formation again? So yeah, this was when we talked about the moon, and we talked about the missions to the moon. One of the big takeaways of the 6 landings on the moon was obviously this giant pile of 800 pounds of rocks coming from the moon that we were able to radiometric date, see that the moon is actually quite old, but that there are various eras that happen on the moon. So the first one is formation and differentiation. And that's the first thing we think that happens with large worlds like the moon, and kind of larger, the Earth, for example. And these are terrestrial worlds, so worlds you can step on. And so the first thing that happens is all the material comes together. It gets stuck together via gravity, usually as that world is moving through the disk of material that was surrounding the sun. and you get kind of a nice sphere. It turns out, like, if you have things smaller than, roughly about 1,000 kilometers or so, you actually don't get a sphere, and that's why, like, things like the asteroids look like potato shapes and weird things like that. They actually were never large enough to actually stay geologically active enough to fully differentiate and turn into a sphere. They actually kind of froze. They stayed geologically active, actually, in some cases, probably almost not at all, or very briefly. And so they kind of stuck together and froze in that shape of kind of sticking together, which is kind of neat. But when you had really big worlds, bigger than, say like the moon or bigger, and actually a little smaller than the moon, probably differentiates as well. Then the material, the planet as it's forming still stays molten because it has all of these radioactive elements. Again, mostly in the Earth's case, thorium, potassium, and uranium that are actually generating heat from the inside. It keeps the whole planet molten, and then the dense material can sink to the very center of the world. So you form a sphere and it sinks to the center. And that's just like when you drop a rock or something in water, it sinks to the center. So the same thing if you got a chunk of iron or a bunch of even like kind of liquid iron, it would sink to the center of the planet. So that's differentiation. That's the first thing. Oh, someone just told me that it's not, their YouTube's not working for them. Oh, I hope that's not the case. Is anyone else on? Doesn't look like actually anyone's on. I don't want to like talk here if like no one's gonna see it. I thought I did everything right. Yeah, it says live now. It says I'm live now. So at least one person couldn't get to it. Well, hopefully they will be able to again. All right. Someone's on again. Okay. Well, I'll answer another question. So anyway, differentiation is the first step. Oh, awesome. Good. I can see Molly's email just there. So differentiation is the first step. The second step is what's called late heavy bombardment. We didn't talk a lot about this, but certainly evidence in the inner solar system where we can see terrestrial surfaces that things were just battered. I mean, that there are impact craters all over the surface of worlds. If you look at the moon or the Mercury, they're covered in impacts and craters. And some of those were really big. The things that formed the large mare on the moon were giant. Probably those hit the Earth at as high frequency, if not higher, than they did the moon, just because the Earth has more gravity, it's a bigger target. But some of the processes that we've just started talking about in geology, the fact that there's plate tectonics, like that there's weathering, there's atmosphere, all of these things act to actually erase surface features and actually erase rock. And so those processes, most of the craters on Earth, there's only like a couple hundred impact craters on the Earth, whereas the moon has, thousands, Mercury has thousands, even Mars has more. But Mars, again, is a pretty dead world at this point. Venus actually doesn't have very many, and that's one of the pieces of evidence of why Venus is still geologically active. But anyway, let's see, Venus. So we think there's a short period of probably about 500 million years, maybe even shorter, where all of the material that's left from the formation of the solar system, the big chunks, like rains down on planets. It goes everywhere, and that's something that we think really happens quite frequently in probably most terrestrial systems, like not just our solar system, but beyond. We call that late heavy bombardment. The probably the third stage, which is most important, is the geologic activity, and that's where you still have radioactive material in the mantle of the worlds that's producing heat, and that heat allows you to have mantle convection that we briefly talked about yesterday. And as we'll see starting tomorrow, that mantle convection allows you to actually have movement of plates and plate tectonics, and that becomes important not just for like movement of continents and yeah, but it actually is super important to like atmospheric cycles, all sorts of cool things, both the water cycle, the carbon cycle that we'll talk about much more next week. And so being geologically active does a lot of things. We also talked about yesterday, being geologically active is probably important in generating a magnetic field, which at least for us as humans is vitally important to protecting us from some of these high energy particles coming from the sun. So geologic activity is the kind of third stage, and then the big chill is the last stage. And that's when geologic, the material that keeps a world geologically active, the radioactive elements just run out, and usually that happens again in larger worlds. It stays geologically active much longer than smaller worlds. So those are the 4 stages. I'll repeat them very quickly. It's like formation and differentiation, late heavy bombardment, geologically active, and then the big chill, just dead. Something like the moon, Mars, now Mercury. All of those worlds are pretty much dead now. I'm going to go to Molly's question here, who says she can't, for some reason, chat, which is too bad. But the email works just fine, Molly. So Molly wants us to go over questions 6 and 8 on the homework. So I had it up in PDF form here. Let's see. Okay, 6. I just don't remember the numbers. Oh, 6 and 8. Okay, so 6 is this table here where we have the 3 fake planets with their Star Trek names, Kirk, Spock, and McCoy. And I give you densities, moment of inertia factors, sizes, and distance from the star. And I don't know if there are any specific questions about one. Hopefully those are all like terms and things that you're familiar with. And this is a format of like asking questions on a homework and certainly on exam that I really like. I like giving students kind of fictitious or fake planets or stars or whatever we're talking about, galaxies, and then giving you various properties and then actually testing whether or not you understood the concept. So rather than just going and like memorizing the properties of existing planets, or memorizing a bunch of numbers, I want you to actually know how things work, and then I'm going to make up the numbers and see how you get them. So let's look at 6 for a second. Usually I would be more interactive if we were doing this in an office. I might even have you, ask me, or I'd ask you questions, but this is the way we're doing office hours now, since I have childcare responsibilities at the moment. Let's see. So the first thing, density of Spock is the first part of 6. And so what I'm really trying to get you at here, right? Like from just like basic things, I don't give you its mass, I don't give you its size, so you can't calculate the density. But what you can do is you can look at its size and really its distance. And what I tell you at the beginning of 6 is all of these worlds are terrestrial exoplanets that are orbiting a sun-like star. So it's a star just like the sun, and these are worlds that you can step on. And if you remember, when we talked about the condensation sequence, when we talked about that, how planets form, we talked about how planets near the star can form from things like rock or really iron, and then iron and rock, and then you have to get beyond the snow line before you really get a lot of ice, maybe just before you get a little bit, but really you don't build really big worlds until you get beyond the snow line, because there you can build worlds with rock, iron, and ice. And what I would hope you remember is that you go farther away from the star. There was a nice plot that showed density as a function of distance in our own solar system for terrestrial worlds. And what you saw is that as you go farther away from the star, because less dense materials condense farther away from the star, as you go farther away from the star, you're starting to add less dense material to the ingredients that you can build planets from. So, nearby the star, you can only build material with build planets with dense material. So, Mercury is like a big chunk of iron with a little bit of rock. And as you go farther away, you can now build things with a little more rock. So you get worlds like Venus and Earth and Mars. And then as you go farther away, you now begin to build worlds with like ice and water and mixes of rock. And so that was the concept I was trying to get you to like remember in part 6A. And so that what you see is that Spock is the farthest planet away. It's at 2.9 astronomical units. And it's a terrestrial world because all three of them are. So its density has to be less than Kirk's. Now, I'm not looking for here you to say, oh, I know it's exactly 1.2 or 2 grams per cubic centimeter. All I really care is that you know that because it's farther away than Kirk is, that it has to be lower than Kirk's density to follow that kind of typical condensation. Well, and if on an exam, we might even ask you why. Like here, we just want to say like, what's the density? But there might be a piece of the exam that's like, explain your reasoning. And the reasoning here would be, it's got to be less than 3 grams per cubic centimeter because it's farther away from the star and the we know that planets that are farther away are going to have more and less dense material to build from which to build planets. So hopefully that makes sense, Molly. You can let me know if it doesn't. Part B, if Kirk and McCoy are geologically active, what's the size of McCoy? So this was another one where there was a trend that I asked you to try to remember, and you'll get it before the exam if you didn't remember it from class. But that is that worlds that are larger tend to be geologically active longer, right? So that and that was due to kind of 2 factors. One, just like the bigger worlds have more radioactive material from which to generate heat, so they stay active longer. But the bigger worlds actually act like insulators, so there's more insulation on the larger worlds. And so, when you go to look at this table here, you can actually see that Kirk is 0.6 times the size of the Earth. I don't give you what McCoy is, but if both Kirk and McCoy are geologically active, then I think it's a pretty good bet to say that McCoy must be like about the size or larger than Kirk. So 0.6 or larger. Now it's possible it could be a little bit smaller because I don't give you what that boundary, but of course I tell you that Spock is 0.5. It's a little bit smaller, and we assume it's not geologically active because I would have said all 3 are geologically active. So I think the answer here really should be something like 0.6 or larger, because you know that Kirk is geologically active at that size, and we know that worlds that are larger are geologically active longer, or it could be the same in this case, and that would be your reasoning based on size. And what are Kirk and McCoy made of? Hopefully this is easier. That McCoy has a density. McCoy's the easier one, I think, of these 2. McCoy has a density of 6.2 grams per cubic centimeter. So it's probably some combination of iron and rock, right? It's got to be at least iron to get that high, and probably some rock too. Kirk's a little harder. So I made Kirk actually intentionally a little more challenging. Kirk is a density of 3 grams per cubic centimeter. So you might say, oh, rock, right off the bit, right? But if you look carefully, the moment of inertia factor tells you that it's not uniformly rock, right? Moment of inertia factor, remember, is at 0.4. That would be everything is uniform throughout. Doesn't mean it's necessarily the same material, but it's uniformly distributed, okay? So for this world, we know it's not uniformly distributed. We know that denser material is at the center. So if I made it exactly 3 grams per cubic centimeter, it can't be just rock because you have to have some denser stuff at the center. So this probably is some combination of rock, iron, and water, rock, iron, and ice to get you to 3. You need something that's denser at the center, but then you need, like, say that's iron, but then you need something to balance that high density of iron to get you back to 3. So this is probably some combination of rock, iron, and ice. And actually, that would be the right answer. Like if this were on the exam, rock would be actually a wrong answer in this case. What are the 4 stages of terrestrial planet form? Oh, that's 7. Sorry. So that hopefully that's 6. Molly, you'll let me know if that's not correct. Question 8 was the other one that Molly wanted to go over before I go over to the other questions that people had. Question 8 is if you were to look through one of the most powerful, very powerful telescopes discussed in class and see a red galaxy, what would you say about the ages of its stars? Is there anything you need to know? Explain your answer. So in this case, on question 8, I'm asking you to a couple of things. In fact, this question is one that's like not straight from lecture because I'm trying to have you put together a couple of different concepts. And I actually came up with this idea because several people have actually either come up to me after class, like when I answer a bunch of questions, and asked me something about this, or they've actually emailed me questions, which everyone is always welcome to do, actually about this type of question. So I thought this was a cool one for like the whole class to think about. And the idea here is that, as galaxies in the universe are far away, the more distant ones, of course, are moving in this expanding universe. And as we saw in Hubble's law, the more distant ones are moving faster away. And so when they move faster away, they are being redshifted. Remember, and that's how we know they're moving far away from us, is their light has actually gotten, or faster away from us, is their light has actually gotten redder. They're coming towards us, it's bluer. And actually, the faster they move, the redder the light is. And so you could presumably imagine a galaxy, and not imagine, I mean, I've seen these, where you have like a blue galaxy that's moving so fast away from us that it actually looks red. Right? And that's what I'm trying to get you to think about in this question, is that, you observe a red galaxy. Do you know that it's really red, or could it be blue? One thing we did briefly talk about in class is that most spiral galaxies are kind of newer formed galaxies. In fact, the one example I showed you to kind of think about this type of thing was like, I showed you a nice blue spiral galaxy and asked, what do we know about this? And we, as a class, we kind of said, oh, this must be a young galaxy because it's blue. And if it has blue stars, we know blue stars have to be young because they don't live very long. So the idea of this is that, if you have a spiral galaxy that's pretty far away, it could actually be very blue. Like it could have no red almost at all. But because it's the part of the galaxy or part of the universe that's expanding so quickly, it looks red. And so, part of this is what you would really need to know is you would need to know how far away this is and how much has its light shifted. And that's actually how we, as astronomers, do this. We look at galaxies and we take an image of them, or we might even take a spectrum of them to see, what type of elements are in them. And when we do that, we have to then shift that. We have to shift it back to what we call the rest frame, pretend like it's not moving. And so we have to alter the colors that we observe based on the movement of the galaxy. So what we do is we actually we take many images of a galaxy in lots of different colors, and then we shift those colors depending on how fast it's moving. And then we might be able to say, oh, indeed, this galaxy really is red, and wow, it's a bunch of old stars. Or we could say, oh, it just looks red because it's moving so fast away from us, all that blue light has turned to red. And so that's what you would need to do. And you can't really say anything about the ages of the stars until you have done that first correction where you correct for the redshift. And the reason I asked this is I really wanted people to think about this question. I think there was a confusion that like, okay, red things are red because they're moving away from you. And the answer is no, some things are red because they're just red, right? Like they're made up of old stars or red giants or things like that. Some things are blue not because they're moving towards you, but because indeed, like they're just blue. All right. But it is true that sometimes you can get some of these galaxies moving so fast away from you that blue things turn to red. And that I wanted you to like see that there are two things happening in this, right? That blue things are often hot, red things are cooler, but that like there's this other effect that can alter that. So there's two things going on. Hopefully that answers your question, Molly. If I write something, test. So it works, but I don't know if anyone else can text in. There was one last question from earlier. Let me go back to it. So I guess if people are watching and want to email me more questions, I'm happy to do it. And Molly, if there's anything you want me to do for follow-up, please let me know. Okay, the last question that I got from earlier was, can you explain the life cycle of a star again, and how and when elements are made? Okay, yeah, sure, I'd be happy to do that. Let me hold on a second. I want to get my 2-year-old to stop banging, so I'll be right back. All right. Thank you for bearing with me. Doesn't want to nap. Anyway, explain the cycles of a star. So I'll explain the cycles of a star like the sun, and then we'll see how that's different with other types of stars. So, with the sun, all stars are only stars when they fuse hydrogen at their centers. Then they're on that main sequence on the Hertzsprung-Russell diagram. And that's really what a normal star is. It's a star that has gotten hot enough at the center to fuse hydrogen into helium. And in terms of that reaction, all I care that you guys know is that you take 4 hydrogen atoms, you smash them together, they turn into 1 helium atom, and then some energy, and there's some other particles that you don't need to know the names of or anything, but that's how you get the energy out, and you've turned hydrogen into helium. And normal stars, that's all they're doing. Okay, so all of the stars in the sky that are kind of in their normal main sequence state, that's what's happening. But when a star ends its life, when it runs out of gas, again, stars are just like cars. They eventually run out of gas. So for a big star, that could be 1 million years. For the smallest stars, that could be 1 trillion years, literally. And for a star like our sun, it's about 10 billion. And we're about halfway through that, right? We're 4.567 billion years into our sun's lifetime. So we're about halfway through the sun's life. And at the end of that, what happens to a star like the sun is the sun stops smashing together hydrogen into helium, which creates energy and actually keeps the sun hot and kind of expanded. The sun actually collapses, and during that collapse actually gets crazy hot. And when it gets crazy hot, sort of like our sun will actually re-expand and actually expand a lot. It actually gets about the size of the Earth's orbit. And that becomes a red giant. And we think most stars actually probably go through that phase, all except for probably the very most massive. We've, of course, never seen the lowest mass stars do that because they take hundreds of billions to trillions of years to do that. And the universe hasn't been around that long. So every tiny star that's ever been born is still alive, barring catastrophic destruction by a black hole or something like that. You get a big red giant phase, and what happens is in that super heated core of the red giant, the reason it expanded so big, it's in that superheated core that you're now able to generate even heavier elements. So in red giant cores, you can take those helium atoms, you smash them together. So you smash, say, 3 helium atoms together, and you get a carbon atom. I think that's actually one of the homework questions. You smash a carbon atom with a helium atom, and you get oxygen. You smash, carbon with a proton, and you get nitrogen. In that red giant phase is actually where all the cool chemistry happens. It's like why we have chemistry. It's why you had to take chemistry in high school, is because we have red giants. It's why we live here, right? It's why you and I exist. It's why we can breathe the air we in. It's because red giants created the heavier elements through a process of nuclear fusion in their centers. And it actually happens in a cool way. First the helium. So normal stars are transferring hydrogen to helium. And then what happens is it gets hot enough for helium to start smashing together to form usually Carbon's the next thing. And then you actually get a whole collapse again. The outer part of the red giant stays pretty stable, but the inner core actually recollapses again and then expands, heats up again. And now you can start to form oxygen. And then that happens again, and now you form, neon or whatever is next. And you actually build up these shells. I think I had one of the slides actually showed that, where you can actually have, iron being made at the center, and then silicon on top of that, and neon on top of that, and oxygen on top of that, and carbon, and so on and so forth. You can actually build these shells, and you actually still can get hydrogen turning into helium on the very outer shell. Anyway, it's really cool. But that's, for me, that's one of the, most important stages of probably this whole class, just because it's what sets up all of the elements that make planets, that make humans, that make life, that make all that. Anyway, after that, in the sun, the outer layers of the red giant are expelled. It's actually very gentle. It's not like a massive explosion. The central part of the core, when it runs out of fuel, actually just collapses, and it turns into what's called a white dwarf. There's no more pressure than really holding up the star, but the outer layers, again, at 1 astronomical unit, are so big that actually they don't actually gravitationally collapse. There's not enough gravity to pull them together. And so they go just puff off into space, but they make some pretty cool shapes. Those are the planetary nebula. Sometimes they're spherical, but sometimes they make these really elongated, awesome shapes. I mean, it's worth Googling planetary nebula and just looking at some of these beautiful shapes. And those shapes we think are due to actually the magnetic fields of the stars, because a lot of the material in those planetary nebula, the gas that's left over from the star actually gets ionized. And all ionized mean is that you blow the electrons off the atoms themselves. And when that happens, you are left with charged particles, which then interact with the magnetic fields. And so if the magnetic field of the star had some shape, the gas that's left over from the outer layers of that star follows those magnetic fields, and you get really neat shapes. I mean, it's worth looking, and beautiful colors. So that's what happens to the sun, and that's really kind of it. The sun then is left as a white dwarf, which is going to be a star, an object. It's not really a star anymore. It's an object that's, about the size of the Earth and a little less massive, about 60 to 70% the mass of the sun, at least for a star that starts the sun. Hold on a sec. William, can you please go to the other room? This is my son, William, everyone. Can you say hi?
Hi.
Hi. Okay. So, can you... I'm talking to students. All right, sorry everyone. So that's what happens in the sun. White dwarf is the final product, and it just sits there and cools forever into basically nothing. It's a chunk of whatever's left over. It's usually actually mostly carbon or oxygen rich, because it's the core of that core that was making all these heavy elements. So it's actually full of all these heavy elements. Some of those heavy elements get dispersed in the planetary nebula, but a lot of them are actually retained in that core of the white dwarf, which just stays there forever. It's actually a terrible end. But for more massive stars, for stars that are about 8 times more massive than the sun, those stars actually explode in a supernova when they go to collapse in one of those stages. And it may be the last stage, it may be an earlier stage of that collapsing and reheating, but often for the most massive ones, it's at the very end. I'm sorry, I'm gonna have to take him. You need to come. You can't play with your train song finish. Here. Here's the train. Please do. Someone wants to play with his trains that are in here. So I might move if he comes back. Oh, someone left. Whoever was watching left. Anyway, I'm sorry if I chase someone away. This is what happens sometimes. So where was I? Giant explosion and supernova. This happens And this is probably, whereas in the red giant phase is where the elements are made. It's in the supernova explosion in only the most massive stars that um, that the elements are distributed back into the galaxy. And I think that's actually one of the really coolest things that happens, right? It's like the ultimate in recycling projects. You have the you have stars that are making these elements, they die, and then for the most massive ones, they explode and they send their material back into the galaxy, and then new stars form from that same material. So for the most massive stars, they explode. It's a violent explosion. I mean, it blows material. And if our sun were to go supernova, which it won't, it's not massive enough, but it would destroy the planets. Certainly all the terrestrial planets, and I think even most of the gas giants, maybe like Uranus and Neptune might survive, but probably not even. I mean, it's a violent explosion. The material that once made up the stars essentially just blown out of the system in a massive explosion. And what's left, in most cases, is what's called a neutron star. And this is actually usually just very dense compressed neutrons that are left over from this explosion. And it's about the size of a city, 10, 15 kilometers in size, but about the mass of the sun is left in that, maybe a little less. Because remember, these stars start as like at least 8 times the mass of the sun. So most of that mass gets blown out into the galaxy, and then there's a little bit left. What's little left stays in this neutron star, and also then just kind of cools to nothing. But they're crazy dense objects. Have enormous surface gravity because they're the mass of the sun, but super tiny. So that I think is pretty cool. And then of course, once you have stars that are 25-ish times the mass of the sun, when that you often get a supernova. In fact, most cases, except for probably the most massive ones, you get a supernova. But at the end, that what's left is actually even too massive for neutrons to kind of hold up the gravity, and it actually becomes a black hole. Space curves in on itself, and it becomes a black hole. So that's all of the different stages of a star. I mean, you could actually say that these little tiny M dwarfs, the little tiny stars, that their end stage is just to still be stars, because again, the ones that are forming now are going to last for 1 trillion years. Universe has only been around for 14 billion years, so these things essentially last forever. So I think when some people talk about the end stages of stars, for the least massive stars, they essentially just say those ones aren't ever going to die. But in reality, they really will die someday. So I hope that answers your question. I mean, I guess the two fundamental things that I really wanted you to get out of that part of the class were, one, that, I guess 3 things. One, I wanted you to know what happens to the sun, because I think it's, what we live around, and that's key. The other thing is I really wanted you to know that, it's that in the bellies of these kind of dying stars is where most of the important elements are. The elements that are important to life, to making us breathe, that our genetic code is written on. I think that's a really cool concept. And third, that the way we actually distribute those back into the galaxy is through these massive explosions of massive stars. Like the sun will not make very much heavy elements. It's not big enough. It might fuse some hydrogen or some helium into carbon, but it's probably not going to do much more than that, just because it's not massive enough. And certainly, even if it makes some carbon, all that's just going to go into its white dwarf, and it's not going to share that with the rest of the galaxy. So the sun's kind of pointless. I mean, it's great for us, but in terms of helping the rest of the galaxy enrich its heavy elements, it's not doing that. But for me, it's a really interesting thing to think about, that we had to have been in a part of the galaxy, and we had to be born in a time in the galaxy when there was enough time to enrich it, right? So that the galaxy is constantly, when the galaxy forms, it's mostly hydrogen and helium, and then it's stars that by turning into red giants and then exploding, actually give the galaxy its oxygen and its nitrogen and its carbon. So it's not only this recycling event, but it means that like at the very beginning when the galaxy was formed, you couldn't form planets, right? Like there's no iron to build planets. There's no rock. Rock is mostly, oxygen, iron, silicon, magnesium, right? Those are like the four main elements in the earth. Like there's none of that. Like stars haven't been around to manufacture it, right? So there's no water, right? You need oxygen to make water. So there's like nothing interesting early in the universe, in the galaxy. You have to have stars that are repeatedly like forming, building heavy elements, exploding, new stars forming from those, exploding, new stars forming from those, exploding. I mean, I've seen some cool estimates on like the sun must be at least a fifth or sixth generation star, right? Like in order to get the amount of oxygen and carbon and iron that we have in our sun and in our solar system, um, many generations of stars must have existed in this area of the galaxy prior to our sun forming for that to happen. And we know that the universe was about 14 billion years ago. It started. We haven't talked about it, but we think the Milky Way formed about 10 billion years ago, and the sun only formed 4.6 billion years ago. So the sun was born after the Milky Way had already been around for over 5 billion years. And so that gave the Milky Way galaxy a lot of time to get more enriched with heavy elements so that it could actually build things like planets. And I find that, again, that's the takeaway I want people to have from this portion of the course is I don't care that you know all the details of stars and stellar evolution. I want you to be amazed that like that we really are made of stardust. That sounds trite and maybe you've heard it a million times, but I find it still amazing that like, the atoms that make us up, the atoms in which we, that enter our lungs in every breath, were once like deep inside the core of a red giant. And then it probably took a supernova to distribute those back into the galaxy. Like that's pretty awesome, I think. And just it's something to really think about. So a very long answer to those quick questions. My 2-year-old appears to be happy, so he's not going to bother us anymore at the moment. Let's see. I have no other questions from email, and no one seems to be able to chat. So I'm hoping this is working. So if you have other questions, anyone else send emails, let me know. It's possible this time wasn't really good, or maybe you're off doing something else interesting. Like I said, I will try to do a couple more of these if people find them useful. We had quite a few people last night who asked some really good questions. So I don't know, let me know. I'm going to be here for another 15 minutes or so. So as people have questions, I'm going to monitor my email, and I'll monitor the chat room here and see if there are any other questions. So, and if I don't say anything, don't be worried. I guess the other thing I would add for those of you who watch this later, it doesn't look like anyone's on at the moment, but I know some of you were planning on watching this later if you had class or things like that. You'll probably hear me say this on the last day, but if I forget, I know a lot of people, there are certainly some like older students in class who are just finishing up their science requirement, but there are a number of students I know who this is your first or second year at Tufts. And being as I spent a long time in college, and then I spent about eight years as a professor over at BU. I can tell you, like, one of the things that I think is really important for new college students to do, and I wish someone had told me this, even if they'd told me at my second or third year of college, is like go talk to your professors, like learn what they're doing. I mean, one of the cool things about being at a place like Tufts is that your professors are all scholars. Like they're not just teachers, right? For most of you, your teachers in high school were teachers, and some were amazing, but they weren't, for the most part, scholars, like really furthering the knowledge of the field. And I think that's a really awesome part about being at a university, is that your professors are there not only to just teach you, but they're also there to like further learning in their specific topic. And all of them are world experts on some topic. And so, I encourage you, go to their office hours when you're taking a class from someone. Certainly ask questions that you don't know about from class, but also ask them what work they're working on. I can always tell people who know about university life when you ask a professor what they teach. That's maybe belies that they don't really know how the university system works. Whereas if you ask a professor what they work on, it makes it show that you understand that they are not just teaching, but they're also doing scholarly work. They're doing research. They're running a research lab. They're writing a book about something, all in the pursuit of learning more about some subject. And so, I encourage you to not only maybe be a part of that process. I mean, a lot of these professors need students to help them do their academic work. But also like ask them what they're doing. I mean, have that be a part of your learning experience. I think that's certainly like it was a very enriching part of mine as both a student and a professor, was having students be a part of that learning process. So I encourage you all to do that. I think that's a key part of this process. So that's my 2 cents. I just think that's something like not a lot of people maybe fully realize until it's too late. So my 2 cents. Let me know if you have more questions. I see people popping in and out. So if you have more questions, let me know. When I'm finished, I'll come play with you.
No, I want to play right here. No, I want to play in here. That's where I was playing. No, I want to just play.
All right, new venue. I'll just continue to monitor the email questions and look at the chat. Hopefully it's working. And hopefully this is useful to people. I don't mind doing it. I'm happy to do it. Like I said, another couple times. I was going to do it originally tomorrow, but I figured it's Valentine's Day and people actually might be doing things related to that. Don't know. And maybe some of you haven't even looked at the homework yet. That also wouldn't surprise me because I'm not sure I would have when I was a college student either. But some of you are more diligent than I think I was. All right, I'm going to wait a few more minutes just to see if there's any last stragglers. I'd hate not to be there if someone wanted to chime in for like the last few minutes and ask a question. Um, so I'm just going to chill right here and uh, we will wait and see. I'll keep monitoring like I said, I'll keep monitoring the email and the chat room. Maybe I'll actually. Here, I'm gonna do a little practicing. I'll turn the sound off so you don't have to hear me. Maybe we'll have like a bonus question of like, what instrument does Professor West play? I actually play the trombone tonight as well, but I've been learning the banjo. But here you go. I'm gonna mute it so you don't have to hear me here play. But I'll play for a few minutes while you guys see if there's anyone else who comes. Okay, given there haven't been any other people writing in or any new emails, I think I'm going to call it. Thank you for those of you who wrote in questions or were on listening. I hope you enjoyed it. Please keep the questions coming, both in class. Feel free to stay after class. I'll be there. I'm happy to stay, half an hour or so after class. I'm happy to answer any questions over email. And I'm certainly happy to do this again if some people find it useful. So have a good rest of your day. Hope you're staying warm, and I'll see you guys all tomorrow morning. Bye.